Okay, let's start our lecture today. Good morning, everybody. And I'm going today to discuss some, in my opinion, maybe most important items of our exam program. And first thing that I'm going discuss be a vector subspace, the notion of vector subspace. What does mean vector subspace? And more generally, what does mean vector space? I recall that the abstract vector space is a some set. Oh, welcome. Good morning. Vector space be some arbitrary set V, which has two operation, abstract operation, so-called addition and scalar multiplication. Addition is maybe enough abstract correspondence, which corresponds to ordering pair of vectors, some vectors, some element of this set. And second operation, which is called scalar multiplication, this operation is simply a correspondence between ordering pair, first element of this pair, scalar lambda, and second vector A. And we have some correspondence which corresponds to this pair, some vector of our vector space. And addition, we have two vectors A and B, and we obtain third vectors A plus B. And this operations are satisfied some 8 axioms, 4 axiom of addition, 2 axiom of scalar multiplication, and 2 axiom, so-called axioms of distributivity, which define connection between these two operations, namely distributivity 7 and 8 axiom if we have some scalar lambda and two vectors A and B, and we have scalar multiplication lambda on the sum of these two vectors. We have the equality in right hand. We have sum to product, scalar product lambda times A plus lambda times B. And if we have two scalars, lambda and mu, and some vector A, and we have scalar product of the sum of such scalar and vector A, we obtain the sum lambda times A plus mu times A. Sorry. And this abstract matter is called vector space. And we have some examples of vector space. I recall that maybe more simple, maybe most important example of vector space is the so-called arithmetical vector space. If we have some abstract field K, for example, K may be a real numbers field, or complex numbers field, or rational numbers field. And we denoted by k up n the set of the ordering n tuples a1, an, where I belongs k. I goes from A to n. And on this set of ordering n tuples, we can define the operations. Addition, if we have two n such tuples, b1, bn, its sum is defined as a sum of corresponding elements of this n tuple. And scalar multiplication, if we have some scalar, some element of k lambda and n tuple an, a1, a2, an, the scalar product of this number, of this scalar and this vector is the vector which is a tuple which corresponding element with this vector is a product of lambda and the corresponding element of this n tuple. Easy to see that in this case we have all 8 axioms, and we before check this assertion. This first, maybe most important example of the vector space. If we have abstract vector space V, and if we choose in this abstract vector space basis I call be a generating linearly independent system, and we suppose that exists in this vector space such ordering system of the vectors basis. If such system exists in our abstract vector space, we can consider the mapping, which is called phi sub e, which goes from our abstract vector space to the Kn. We suppose that our vector space is defined our some field K, and we have the following mapping. If we have abstract vector A from this vector space, we can decompose this vector on this basis. We can present this vector as a linear combination of the vector of the basis. Namely, we have the following presentation of our vector. By definition of the basis, such presentation exists and unique from the fact that the basis is generating system. This fact, it follows that this presentation exists and linear independence of this vector from this linear independent follows that this presentation is unique, and we obtain uniquely defined coefficients of this linear combination, and we can correspond to these vectors the ordering n tuple of these coefficients, and this n tuple will be the element of our arithmetical vector space, and we obtain this correspondence. Easy to see that this correspondence respect to the operation on this vector space and arithmetical vector space. Namely, if we have sum of two vectors, A and B, we correspond on these vectors A and B the decomposition of this vector on the basis, and easy to see that if we present vector A as a linear combination of the basis vectors, and we can consider the same presentation for the vector B, using the axiom of the vector space, the sum is equal the following sum. And easy to see that the sum of corresponding coordinates of this vector A and B, B is the coordinates of the sum of this vector. And we obtain the following correspondence: A1 plus B1 and so on, AN plus BN. And by definition of the operation addition in the arithmetical vector space, this ordering pair is the sum of the coordinates of the vector A and vector B. By definition, this sum is the phi from A and phi from B. And we obtain the following property of this correspondence: phi A from A plus B is equal phi E from A plus phi E from B. And we can see that this correspondence preserve this correspondence respect to the operation sum on this vector space. In the same way, we can check that this correspondence respect to the scalar multiplication. We have the following equality. And we obtain that this corresponding, this mapping respect to this operation, and this property can be called homomorphism. Then if we have some abstract correspondence with respect to operation on this algebraic on this set with algebraic operation, such a correspondence called homomorphism. But this correspondence is bijective, one-to-one correspondence. Easy to see if we have any an ordering and tuples, arbitrary element of the arithmetical vector space. To this element corresponds some vectors from this vector space. Easy to see if you consider some arbitrary element A and A n, we can construct the vector by the formula A I EI, and this vector is the element of our vector space V, and this element corresponds to this arbitrary n tuple. And this fact is essentially that this mapping is surjective mapping. And we have different vectors A and B, and these vectors is not equal one to other. These images also be different, because its difference is not equal 0. This simple example, we show that this simple example is essentially enough general. If we have arbitrary vector space, we can consider this canonical mapping and pass to this arithmetical vector space. We can consider this arithmetical vector space as a so-called maybe universal vector space, which can be considered as the image of the arbitrary vector space if you consider this this mapping, but remark that this mapping is not canonical. This mapping depends from the choose of the basis. We have many such mappings. If we change the basis, we obtain the other mapping. Okay, that other example of the vector space, in my opinion, enough important, the vector space of polynomial. If we have now let's fix some field K. For example, K may be a real number field, and we can consider the set of polynomial the element of the set is an expression of the following type, and we can such expression as functions also defined on our field K, and we have two such functions. Oh, I'm sorry, B0 and BM, we can consider these two expressions. We can consider that n is equal m. If m greater or equal that m, we can consider the new elements which is equal 0, and we can suppose that n is equal m, and we can define the sum of this polynomial as a polynomial which has coefficients. Oh, I'm sorry, B1 is the sum of the corresponding coefficients of the summons polynomial, which is summons. And by the same way, we can define the product of the scalar lambda on the polynomial by the following formula. And easy to see that we obtain the sum, we obtain the vector space. Easy to check that all axioms. And we obtain the example of the so-called infinite dimensional vector space. In this vector space does not exist the finite basis, but we can fix the degree of the polynomial and consider the polynomial degree less or equal some integer n. By definition, this polynomial from kt such that degree of this polynomial less or equal n. Easy to see that we obtain the other vector space, and this new vector space is subset of this vector space, and respect to the operation of the initial vector space. And we can generalize this example and consider general definition vector subspace. Let V be some vector space, our some field K, and let U be a subset of V. If V itself a vector space respect to operation of initial vector space V, in this case U is called vector subspace. How to check that the some abstract subset, some subset of initial abstract vector space be a vector subspace? The direct way to check all 8 axioms, but part of this axiom is satisfied because this some part of this axiom is true for subset, because this axiom is true for all vector space V, and we no need to check this axiom. And we have a more simple way to check that some subset is a vector space respect to the axiom of all vector space V. We have the following theorem, criterion for the vector subspace. In the definition of the abstract vector space, we have a so-called zero axiom. This axiom asserts that on the abstract vector space are defined the operation of addition and scalar multiplication. The fact of existence such operation is an axiom, essentially is a zero axiom, and after them we must check the other 8 axioms: addition, for axiom of addition, to axiom of scalar multiplication, and to axiom of axiom of distributivity. But initial, most basic axiom, the axiom of existence such operation, and the theorem exists that let V be a vector space our field K U be a subset of V. U be subspace if and only if first U be closed addition and scalar multiplication. Namely, if we have two vectors A, B from U, its sum A plus B belongs U. Closed relatively addition. Closed relatively addition. And we have some scalar lambda from K and any vectors A which belongs U. It follows that scalar product lambda times A belongs U. It means that our set is closed relatively scalar multiplication. Easy to see that if U be subspace, the items 1 and 2 of this assertion is fulfilled. But more interesting fact that if these two fact is two items of this assertion is true, it follows that our subspace, our subset U be a vector subspace. How to check that fact? We must to check that all 8 axioms is fulfilled. How to check this fact? Let's prove that these two facts follows the fact that the U be a vector subspace. We must to check the following 8 axioms. The following 8 axioms. I briefly recall these 8 axioms. First of them, commutativity. Second, I'm sorry. First of them, associativity. Second, commutativity. Third, existence of zero. Fourth axiom, existence of opposite element. The axiom of addition to axiom of scalar multiplication. And to axiom of distributivity. Here, lambda is a scalar, A, B, C, B are vectors. And how to check this axiom? Easy to see that this axiom, are true because this axiom are true for all vectors from the initial vector space V. And this fact, from this fact, easy to follow that this fact is true for element of any subset. And this axiom is evidently fulfilled. We have two axioms, existence 0 and existence of opposite element. How to prove this axiom? Existence 0. We have some corollary of this axiom, namely, if we have 0 element of basic field K, and we scalar multiply this element on the vector, any vector A, we obtain the zero vector. From this fact, it follows if we put this number lambda equal 0 and multiply this lambda on any vector A, we obtain 0. And this item, from this item, follows that 0 belongs to our subset. And this axiom is true also. We have last axiom, this axiom. This axiom, it follows from this fact. If we have some element and we multiply this element onto minus A, we obtain minus A. Easy to see. A plus minus 1 on A from this axiom is equal, from axiom number 5, it follows. Let's prove this fact. Easy to check this fact. I try to prove that the sum of any vector A plus minus 1 times A is equal 0 vector A. Easy to see that this is equal product unit element of the field A plus minus and how to check this fact? Easy to see if we obtain 0, 0 A plus 0 times 0 is equal 0 A, because 0 plus 0 is 0, and we can obtain to the left and right side minus and this we obtain the zero vectors, and the right hand we obtain 0 times A, and we obtain this fact. So we prove this theorem. This theorem is proved, and after them we obtain the easy criterion for the fact that some subset be a vector subspace. And we can check that some abstract subspace subset when some abstract subset be a vector subspace. Let's consider some examples of such some subspaces. Examples. Let V be some vector space. Consider the some set of the vectors, some arbitrary set. For simplicity, let this set be a finite. For example, we have some vectors of this vector space. We can consider the set of all linear combination of this vector, all linear combination. This set is called linear span of these vectors. By definition, linear span of this vector is a set of all expression of the following type. I assert that this set of all linear combinations be a vector subspace. How to check this fact? How to check? We must to check to assertion. First, easy to see that if we have two elements of this set, namely two linear combinations, first of them lambda 1 A1 plus so on lambda n an, and second easy to see that the sum of such expression be also some linear combination. Using the axiom, we can permutate this element such way, and we can group this element. And using the axiom of distributivity, we can rewrite the last expression by the following way. And we obtain that the sum of linear combination be a linear combination of initial vectors A1, An. And we check the item 1 of our criterion. Do you understand it? And the same way we can check the second point, the fact that this set is closed relatively to scalar multiplication. If I have arbitrary linear combination of this vector, and if I multiply this linear combination on the arbitrary scalar mu using distributivity axiom, I obtain the following expression. It means that we obtain the linear combination. I use the distributivity axiom and axiom of a scalar multiplication, namely mu times lambda I AI is equal and this axiom and axiom of distributivity, and I obtain this equality. And we obtain the some most general example of the linear span. What does mean geometrically? What is the geometrical interpretation of the linear span? Let's consider the example of the geometrical vector space. Let's consider the geometrical vector space E2, the plane, and let A and B be two vectors in the plane. What does it mean? It's linear span. Let's consider the arbitrary product of this vector on the arbitrary scalar. And the set of such product be the set of all vectors which parallel to our vector B. And the set of all products of the vector A and all scalars be the set of the vectors which parallel to the other vector A. And after them, we must consider the sum of these vectors and these. What we obtain? We obtain the set of all vectors, easy to see. Any vector can be decomposed, can be presented as a linear combination of these vectors and these, can be presented as the sum of the product of some scalar lambda and these vectors and this. And in this case, we obtain that linear span of this vector all the space E2. If we embed the plane in the space, geometrical space, and consider two vectors in geometrical three-dimensional space, its linear span with some plane which passes for the region of coordinate system in the three-dimensional vector space. We can generalize this example and consider some abstract vector space and consider some subset, some final subset of this vector. Its linear span gives us some vector space which contains this vector, this minimal vector space, which subspace which contains this vector. Okay, the second example is a set of solution of some linear system. We have some equation, and we can consider the set of all solutions of this linear equation. Easy to see that for the set of solution fulfilled the items 1 and 2, which the items 1 of 2 of the criterion of the vector subspace. Easy to see that we have two solutions. The sum of two solutions also be a solution. If we have other solution, the sum of two solutions by definition easy to see that also solution of this equation. And because if one of the solutions I multiply into some scalar, I also obtain that this vectors also be a solution of this linear system. And we obtain that this set of solution of linear equation be a subspace. Easy to see that we have the sum set of solution the set of solution of linear system be intersection of the sets of solution of every linear equation. And easy to see that intersection of any set of vector subspace be also vector subspace, because the intersection also closed relatively to the operation addition and scalar multiplication. If also set is closed, it follows that and intersection and also closed is the same. And we obtain as a corollary two facts. First of this fact, that the set of solution of arbitrary linear system be a vector subspace. And second fact, that the intersection of the subspaces is also subspace. Let's formulate some proposition. Let V be a vector space. Vector space U alpha some index be a vector subspace. Then intersection be a vector subspace. Let's check the first property from the definition of the criterion, from the criterion of the for the vector subspace. Let we have two vector A and B, and let this vector belongs intersection. From this fact, AB belongs to alpha for any alpha by definition of intersection. But U alpha be a vector subspace. In this fact, it follows that the vector subspace is closed relatively vector addition and scalar multiplication. From this fact, it follows that for all alpha, for any lambda, for any scalar lambda. And from this, it follows and we proved that the intersection of any set of the vector subspace be a vector subspace. Okay, and we obtain some operation of the vector subspace, operation intersection. This operation coincides with theoretical set operation intersection. And consider the other operation, so-called sum of the subspace. Sum. What does mean sum? Sum is some analogs of the union of the set. What does mean sum? Let V be a vector space. U and W subspaces are subspaces of V. By definition, U plus W. U plus W be the sets all the sum capital U and plus capital W is a set of all sum U and W. U belong capital U, W belong capital W. I assert that set of all such sum be a vector subspace. How to check this fact? How to check? Easy to see. If you have two such sum, let U1 plus U1 be the first element, sum U2 plus U2 be other element of the sum. I must check that the sum of this element also the element the sum. How to check it? Let's consider the sum of this element. Easy to see that I can permutate this element, and using the axiom, I can rewrite this equality as the following equality. Do you understand? how I can this equality using associativity can be rewritten using associativity. We obtain this equality. After them, I permutate these two elements, and after them, I obtain this sum. Final sum. Easy to see that the final sum, this element, the sum u1 and u2, and this element, this both element belongs U, capital U, and this element of the element capital U. And this element, the element of the subspace. And we obtain that the sum belongs to the sum of the vector space. It is this. It means that this set is closed relatively addition operation. And by the same way, we can check that closeness relatively to scalar multiplication. And we obtain that this sum is a vector subspace. Okay, and we obtain two operations on the subspaces. Operation intersection, the operation of the sum. Intersection, sum. Intersection is sum. If we see that this vector subspace belongs U and belongs V, but from other hand, this sum contains U and W, and we obtain the following embedding. We have the following embedding. And let's suppose that U and W, we suppose that V be a finite dimensional vector space. In fact, from this fact it follows that this subspace is finite dimensional and this finite dimensional and this finite dimensional. What about dimensions of this vector space? We have the following important theorem. So-called Grassmann formula. Dimension of the sum is equal dimension U plus dimension W minus dimension intersection. Let's prove this formula. Let's choose the basis in the intersection. Let be a basis add to this vectors, let E be the basis in the intersection. Add to this vector some vectors U1, US, such that vectors U1, US, E1, EK form a basis in the U. Basis in capital U. The same way, consider a new basis and in capital W. Namely, we add to the vectors E1, EK, some vectors U1 and so on, W1 and so on, WR, such that all these vectors form the basis in capital W. Let's denote this basis EW, this UE. The main assertion, the union of this basis, the big system U1, US, E1, EK, W1, and so on, WR, UER, or UEW, be a basis in the sum. Let's prove this main assertion. I assert that this big system be a basis in the sum of the vector space. The main assertion. The theorem easy follows from this assertion. Easy to see if I count the numbers of these vectors. Easy to see that this number, by definition, is equal the numbers of the vectors of the basis. Easy to see, the dimension of the sum is equal S plus K plus R. Easy to see. But the dimension, the U, by definition, is equal U plus K. Mu. And K plus R dim W, and K dim intersection. Easy to see that we have this evident equality. And our claim to prove this assertion. How to prove that this system be a basis? We can check that this system is generating system is enough evidently if we have any vector V which belongs the sum U plus W. It means that this vector I can present by the sum vector u and some vector w. But this vector I can decompose by the basis lambda I ui plus mu g eg plus mu g eg plus he L WL. And after evident permutation, we obtain the following equality. And we obtain decomposition of the arbitrary vector by these vectors. It's enough evident fact. But non-trivial fact that this system a linearly independent system. And the most hard part of this theorem, let's prove the system is linear independent system. From this, for proving all this fact, let's consider the linear combination of these vectors. Our claim to prove that all coefficients of this linear combination are equal 0. The main claim. We can rewrite this equality in the following way. The left side be the element of U. The right side be the element W. And we have equality. What does it mean, this equality? Left side belongs U, right side belongs W. And left and right side are equal. What does it mean? Left and right side belong intersection of this set. It's enough evident. And what does it mean that this expression belongs intersection? It does mean that I can decompose these vectors on the basis of intersection. I have the following equality. This sum is equal lambda tilde I e tilde. And after them, I can permutate, transform this left side in right side, and I can rewrite the last equality in the following form: lambda tilde I plus mu lambda. I'm sorry. Yes. New L W L plus lambda tilde I e I is equal 0. But these vectors form the basis in the W. And it follows that these vectors are linear independent. And by definition, it follows that all coefficients are equal 0. For us, enough the fact that all L coefficients are equal 0. It means that this expression 0. This expression is equal 0. And the left side also equals 0. Right and left hand side is equal 0. But these vectors form the basis in U. And we obtain zero linear combination of the basis vector. That means that all coefficients, these vectors, also equal 0, because this vector is by definition linearly independent. And we obtain that all coefficients, this linear combination, all coefficients are equal 0. Are equal 0. Oh, I'm sorry. Yeah, okay. Oh, yeah. That's right. Maybe better to write mu tilde. Okay, let's. Lambda 1, lambda s, mu 1, mu k is equal mu 1, mu r is equal 0. And we proved that this theorem is proved. Okay. And how to find the sum and intersection of some vector space? The algorithm to find the sum and intersection. For this, we can use the two above-mentioned presentation of the subspace. If U be a linear span of some vector a n and a1 a n, W be a linear span of some vectors b1, bm, easy to see that its sum be a linear span of union of these vectors. Easy to see that by definition the sum be the set of the sum of vector from this space and this space. any vectors of the space be a linear combination of these vectors, and vector from this a linear combination of these vectors. Sum of linear combinations is a linear combination of union of the generating system. And this fact is enough evident. If we have presentation U as a set of solution of some linear system with matrix A and W is a set of solution of linear system with matrix B, the intersection is a set of the vector such that belongs the first subspace and the second, both subspaces. And it means that the coordinates of these vectors satisfied the big linear system, which is a union of the linear system for first vector subspace and second vector subspace. And intersection can be easier found if the subspace describes as a solution of some linear system. And we need to pass from the one way to describe subspace to other way. We have two ways to describe subspace of the vector space. One way presents this subspace as a linear span of some vectors, and second present this subspace as a space of solution of some homogeneous linear system. How to pass from one way to description to other way? One way to second way. One way linear span, second way solution of linear system. How to pass from one way description to other. One way linear span, two-way space of solution. Of linear system. First passage from this way to this way. If we have some linear system how to obtain the basis in the space of solution. We can to solve this system and after them find the basis in the space of solution. We have such algorithm. And if enough easy way from this passage. Opposite passage. We have linear span, some vectors A1, AN. And how to obtain some linear system for which this the space of solution of this linear space, space of solution of this linear system coincide with this linear span. The idea is the following. Let's consider some linear combination of these vectors. The question is, if we have some arbitrary vector in the arithmetical vector space, when this vector can be presented as a linear combination of these vectors. How to understand this fact? Let's suppose that all these vectors can be presented as element of arithmetical vector space, namely like some arithmetical vectors. Maybe n be a dimension of the initial vector space, and m denotes be the numbers of the vector of our linear combination. And we obtain that linear combination is equal to some arbitrary vector of the vector space. I would like to obtain the some condition from these coordinates such that this condition defined that fact that this vector be a linear combination of these vectors. What does it mean? I have some unknowns, numbers lambda 1, lambda m, these unknowns, these variable unknowns, and some given arithmetical vectors a and m. And I can rewrite this equality as some linear system. And in this linear system, lambda 1, lambda m be unknown, and these numbers be coefficients of this linear system. Namely, I obtain the following quality. I obtain the equality of these two vectors. And this equality can be rewritten as a following linear system. And we have the following question. When this linear system has non-trivial solution, has only solution. We have so-called Kronecker-Capella theorem, which was proved on the previous lectures. And this theorem asserts that if rank of this matrix coincides the rank of this matrix, the system has a solution inside them. The system is consistent. And how to calculate the rank? We can use elimination Gauss method and reduce the matrix of this system to the echelon form. In this matrix, after reducing to the echelon form, as a rule, in this matrix appeared the zero rows, but in the right side of the system we have some variables x1 and xn, and in this we obtain some linear combination of these variables. This linear combination we can consider as some linear equation, and we obtain opposite zero rows some linear equation, and the fact of coincidence of the rank matrix and rank augmented matrix is equivalent that this linear combination are equal 0. And we obtain some linear system. And this solution of this linear system is exactly coincide this linear combination of this vector by definition by Kroneker's Capelli theorem. And we obtain some algorithm to find the linear system. This algorithm is following. We can write the matrix, the column of this matrix be coordinates of the vector A1, AM, and on the right side we must to write the sum unknown x1 and xn, and using Gauss echelon method to reduce this matrix to the echelon form, and we obtain some zero rows, and in the right side we obtain some linear combination of unknowns x1 xn, and the equality this linear combination which lies opposite zero rows. We obtain some linear system, and this such linear system, the set of solution of which coincide with linear span of initial system of vectors, and we solve this problem. Maybe any question? Do you understand? Okay. Thank you for attention. And after then we have seminar and some test. Okay. Oh, maybe question? Yes. Yeah. Mm-hmm. Yeah.
And I have a question about the exam.
Oh, okay. Mm-hmm.
Yes. You gave us a PDF file containing 16 topics, and students wanted to know if we can have the cases of any book like previous semester for us to study.
Yeah. For example, on this week I sent the notes of my lectures and some standard exam exercises which will be used on the exam on this week. In the end of, I prepare this standard question, maybe, and today we have some test, and after this test we obtain some scores on the test, and the preliminary scores in the maximal preliminary scores can be 30 scores, and on the exam we can obtain 70 scores, and the rules is the same as the previous exam.
So for the questions,
30 questions and this marks be the sum of two tests and only sum of the two tests, and maybe some scores for the attention of lectures. Yeah.
The question you will send is standard questions.
Yeah. I'm going to send. Yeah.
You'll answer in exam.
Yeah.
Those are the questions that you have to prepare for the exam.
Yeah. On the exam, you obtain some theoretical question from the program and some practical problem. And this practical problem, as a rule, will be coincide with the problem from the list.
Those 16 questions you sent us are for theoretical problems,
Yeah.
right?
Yeah. Okay.
Thank you.
The same as the previous exam. Yes.
By the way, is it possible not to turn off the camera while you're writing the test at the seminar, like with you?
Maybe if you can opportunity to now write to me and okay, but better now to write. Okay.
Thank you.
Thank you.